Our next presentation demonstrates how the district uses rainfall and stream gauge data from our flood warning program to validate models. Please welcome our flood warning manager to the podium, Bruce Rindahl.
Thank you, Alex. We want to talk a little bit about utilizing our flood warning system in for our real-time rainfall models and to analyze and validate some of the models that we have in place. Oh, that's going to be tough to read. Okay. What we first wanted to talk about was our mission, and our mission is to protect people, properties, and that's what we focus on right now with the flood warning system. We protect people. We want to give them ahead of time the warning that a flood might be imminent and do the adequate precautions to get out of the way. What we're talking about now is utilizing that system to move forward so we can use the data to maybe increase our planning and get the abilities to protect other environments other than just the people. First off, what are hydrology models at the district? Well, they're actually really very simple. Traditional hydrology model is a COHP model. You get all the parameters, the basins, the lengths, all the fun things that go into a COHP model. You put a design storm rainfall onto the system, run the COHP, and you get runoffs from all the various subbasins. Then you throw it into SWIM, and you route everything downstream. That's all a hydrology model is, right? It's very straightforward, but what we want to focus on in this program is this design rainfall. What if we took actual rainfall measured from our rain gauges or from a gauge-adjusted radar and put that in the model as opposed to a design rainstorm? What would we get? And that's what we want to try and analyze here. We've been doing this since 2004. You saw some of the real-time models. We've been taking very simplified models of COHP or HEC models and putting them in using real-time rainfall. Now, they run every 15 minutes during the flood season using the measured rainfall, and we can then take a look at what they're forecasting from the existing models that we have from the rainfall that we are measuring in the field. Here's Temple Pond for Goldsmith Gulch. You can kind of predict at various different locations along the basin at the design points what we're expecting to see from the existing rainfall. These are live on our website now. You can then use methods to route them downstream. We use some simplified routing methods instead of SWIM, and we move that further and further downstream so we can get some results. We can forecast peak inflows. We can forecast crests to give us some kind of information about what the flood warning system is telling for the potential impacts. And we can also utilize forecasted rainfall. We just started doing this last year, and we're going to expand on it this year. If we have forecasted rainfall for the various models, what is that going to tell us? So we get a little bit more lead time of what's happening. And that lead time can be incredibly valuable. From where our model ends in Goldsmith Gulch to where we have a really critical flood location, which is the bike paths on Cherry Creek down by Steele, that can give us almost a 2-hour lead time. And we can give alarms, we can get notifications prior to it actually occurring at the location where we have it. So it's very valuable for that, to utilize that. Now, how can we use all the existing models that we have at the district? The real-time models, we have 5 right now. They've been running since 2004. We have a whole lot more of those models that we have in COHP, highly detailed models, very accurate, we hope, models for that, and we want to utilize those and see what can possibly happen. Because developing new models are very expensive and very, very time-consuming, so we want to leverage the ones that we have. First off, very simple, I'll run through this. It might be hard to see, but those little blue dots are where we have alert rain gauges, where we're getting real-time data, every event-driven, so as we get a little bucket tip from the rain, we actually get a sensor of when it occurs. Then we can do some analysis of say, okay, how are they distributed? For those of you who've done it before, they're either Thiessen polygons or Veroni polygons, and we would just say, okay, here's the closest area to any particular rain gauge. And then using some GIS techniques, We can then intersect it for all the little subbasins in a detailed hydrology model. So for every subbasin, we can say, this is what we think the rainfall distribution is for all the subbasins for 5-minute time steps. So now that we have that tool, how are we going to utilize that? Well, we do a little bit of magic with a upcoming CUHP version, which allows a couple things. We've got increased performance for that, and we also have the ability to tie directly into our alert database. So we can say, we want to run this storm on this design basin, and we want to see what possibly happens coming out of the CUHP models. We've set up the framework, so all we have to do is, in the little center of the area there, we specify, I want this model, I want it ending at this time, on this date. I want to either use the alert data or I can use the Gage adjusted radar rainfall data, either one, and it generates the distribution of the rainfall for every single one of those subbasins automatically. It takes about 15, 20 seconds to connect to the database, update it. And then the really difficult / fun part is for those of you who've run CUHP, every subbasin either goes, oh, I want the 100-year storm, I want the 50-year storm, or I want the 2-year storm. These models, every single subbasin has their own rain gauge. And every rain gauge is get a generated rainfall distribution from the database for that. In this case, we just then, once we connect them, we have a rain gauge for each one, and then we use the standard CUHP interface to run it. We're doing a little bit of increase performance-wise, so we've optimized the code that we're working on. It'll be coming out sometime this year, I assume. But we're working with it now to take a look at making the models run with existing rainfall. So we're starting to do this with the storms that hit in 2022. I think you've had a few examples of the storms that hit Tollgate Creek, that hit Niver Creek, that hit Goldsmith Gulch, and these are the storms we want to take a look at. Again, this is what you saw before. We had some pretty significant events in 2022. We had 2 inches of rain. In one location, we had almost 2 inches of rain in 15 minutes. That's the kind of intensities we were finding. So it was a good start to take a look at it, see these models, and see what we can do with them. Some of you may remember these pictures. This was I-70. This was the storm on the 7th. The very intense rainfall. After it came through Niver Creek, like Andy showed you, it then hit I-70 and caused some severe problems down there. Here's what the media put out. On the 16th of August, Broomfield got 3.7 inches of rain that morning in just under 4 hours. I woke up that morning and they said, Bruce, don't worry about it. Today's going to be an easy day. Yesterday was really bad, but it's cleared out. It's cold. We're not going to get a lot of rain. Yeah. So we got that. So we also investigated those storms, and we're putting those slowly into the models and running them and doing a comparison with what we measured. Again, we had some pretty severe events. I think it may be tough to see that there's 2 lines there. The top red line is the design storm, the 100-year, 1-hour storm that goes into your CUHP. The blue line just below that, that's what we measured at Confluence Pond in Aurora during this storm. So up to the 30-minute, we were tracking a 100-year rainfall event. And it just tapered off just a little bit as the storm moved out. So we were really pushing some pretty impressive events. It didn't go through the whole basin, it just went in selected locations. So how are they working? We think they're doing pretty well. We're just getting started into looking at them, but we're getting some interesting results. For those of you familiar with Goldsmith Gulch, this is Temple Pond in the Denver Tech Center. I look at this and I go, that's pretty good. Just eyeballing, the volumes are about right. The peaks are off a little bit, and then we taper off. It stays a little higher than we thought. Is that the model? Is that the outlet works? Is that the volume in the pond? Could be a lot of things, but I'm pretty happy with that. So we're thinking we're going to have some pretty good results for this, and we want to move forward. We also do some quality control. This is the model results at Goldsmith at Eastman. First blush is, well, the model wasn't too good. It overestimated everything. And then you stand back and you go, the model looked pretty good upstream. The model looked pretty good downstream. We really haven't done a rating table at this Gage location in many, many years. So we think there's some scour that goes on. There's some instability. As you can see, the gauge went up and down. So we said, based on this results, we kind of want to look at the rating table in the flood warning system. So it's giving us some benefit, not only looking at the models, but looking at our alert system as well. So, changing subject a little bit, but it's all kind of related. What is the future of NOAA Atlas 14? Well, of course, the easy answer is NOAA Atlas 15. They're just coming out and looking at that and trying to see what we can do and how it's going to be revised and done forward. Now, NOAA did not use the alert data from the district for NOAA Atlas 14. They did hardly any 1 hour precip estimates, but we want them to use much higher low frequency, high intensity storms, 30-minute storms. What will that do in their analysis? So we asked them if they were interested in our data. They said yes. We gave them every single piece of our precip data, every single data point that we had going back to 1986. So we dumped them in the files. We said, here you are. Let us know if you have any questions, and they're in the process of poring over them. And a little plug for us, I don't know if you can read that, but one rain gauge for the period of record, 23,000 data points. It's a big database that we have a very efficient way of getting data in and out. And we have well over 100 rain gauges. So you can imagine the kind of data that we have to process to put through all this information. And it's very difficult it takes a lot of interfaces to make sure you get valuable, clean information for that. We can also do our own analysis. We have the ability to go in that database and say, for every gauge at every year, what was the maximum 5-minute rainfall intensity? What was the maximum 1 hour intensity? And we can crawl through the database, wait for it, and it'll spit it out every gauge in one particular year, or one gauge for every single year that we have in the record. So we can analyze what these peak flows are and what peak intensities are for comparison for something like NOAA Atlas 14. So we can take a look at some results. We do the standard plotting position for intensities. We put it on the graph. The blue dots are our actual measured values that we've gotten in the system over the last almost 40 years. The black dotted line is NOAA Atlas 14 at this location. The red line is a quick and dirty, for those of you familiar, Gumbel distribution of saying that's probably a good distribution for that kind of data. And you can say it looks pretty good. NOAA Atlas is pretty well right on there, and that looks really nice. So we're happy with that. We'll take a look at it. Other gauges, well, it looks like that other distribution is a little better, and NOAA Atlas 14 may be overestimating. Again, we're taking a look, having them look at all the gauges, where we're looking at it, and have their analysis, and when we get some results back, we'll be real interested. And quickly, the last chart, for those of you who remember, and we're going to see some more, 2013, that thing was off the charts. This should get you some perspective of those lower dots. That's where you typically look at it, and that top dot, that's how much a 24-hour rainfall total that we had in Boulder of well over 10 inches. That's how far off the graphs it shows up. So a very, very extreme event. But that's what we're giving them for them, and they'll take a look at it. We're focusing only on the 1 and 2 hour storms for our analysis, our models, and our flood warning system. Quickly, some of the future directions. We want to take a look at all the models that we have and slowly migrate the data that we have in them. We want to look at other analysis for the existing models that we do have. Are they good? Are they bad? All models are wrong. Some may be useful, so hopefully we'll try that. We're very interested in utilizing this to see what impervious area like brick has done for that and how we can improve the models. Some other ideas are moving to the analysis of partial duration series. Will that help us? Or other options that we can to just kind of use the data to see what our models are telling us and where we can go to move forward from that. So it's an exciting time. We're looking forward to working it and having the data not only for our use, but for your use too if you're interested. So thank you very much for your time.